What's wrong with science? Since the new James Webb Telescope's been online, research has thought the bottom. The Flamingo Deep Field image from the James Webb Telescope reveals groundbreaking new physics, but, unfortunately, almost none of the revelations fit our previous cosmological view of the world. Had all of what we had previously thought of the universe been completely wrong? The new images from the James Webb Telescope and the Flamingo simulations have pulled back the curtain on the vast gaping hole in our understanding of the universe. There is an unprecedented crisis in cosmology right now. Both our models of space and of its true origins are in urgent need of revision. Why do we have to wait so long for new answers? Why are so many scientists silent when the latest research comes out? What is wrong with scientists? It's uncomfortable, almost painful, what many scientists and even the greatest in their field are now facing. These guys might be so off, medium man. For so long, they've created a bunch of theories and models that have been based on completely wrong basic assumptions. Now that house of cards on a shaky foundation is coming tumbling down. For the most part, younger researchers are adapting more easily to the new findings. Excited, they are following every current development, and many are tinkering with new worldviews. Other branches of science, however, are setting out to ignore what can no longer be denied. Our universe is much older than previously thought, and is not as we had imagined it. We didn't have a Big Bang 13.8 billion years ago. We very probably did not. The first stars weren't massive, single stars that would quickly burn out. Perhaps our cosmos never knew of the Dark Ages. But all of these assumptions, all these previously basic assumptions on this basic cosmological model, they could be wrong. While modern cosmology has great difficulty in measuring the age of the universe, despite ever-improving methods, the problems are mostly attributable to two other methods alone that sometimes result in totally different interpretations. One way is to observe the cosmic microwave background radiation, the remnant of the Big Bang that's supposed to give us clues about the earliest phases of the universe. These measurements tell us the expansion rate of the universe, called the Hubble constant, that in turn helps us work out the age of the universe. The other method depends on the observation of events, such as certain types of supernovae whose absolute brightness is known. Their apparent brightness can then be compared to known absolute brightness, and the distance, and therefore the expansion rate of the universe, can be calculated. But these two methods come up with a discrepancy, or a Hubble tension problem. The observation of the microwave background radiation in general points toward a greater age of the universe than do, say, observation of the supernovae, the exhausted, career-end products of stars, which seem a lot easier to get a fix on. Scientists sometimes fight strongly over these differences. On the other hand, they could indicate one or a few new physical phenomena we are not aware of yet, and therefore have not taken into account in our present-day cosmological concepts. Assimilating new worldviews is no less important here than the building of a consensus of many different branches of science. James Webb proves something else in the world of cosmology. An era of discovery has begun with the James Webb Space Telescope, which has imaged what look like the brightest light sources in the universe, their light 1 billion times fainter than anything ever visible before. Now, some of our deepest cosmological models and theories are being painfully put to the test. The standard model of cosmology has been almost untenable, known as the LCDM model, since these discoveries. Based on the existence of dark matter and dark energy, this model already explains many cosmic phenomena, from the structure of the microwave background and distribution of cluster in galaxies. And yet, yesterday's James Webb Telescope observations have left questions, some perhaps not fully in accord with our current notion of dark matter and dark energy. Then there's the fact that we didn't, for all practical purposes, even know what dark matter and dark energy are before the latest findings. They were pure assumptions. This is why some scientists are now struggling so much to admit we have built up our basic cosmological worldview based on scientific speculations, which later turned out to be truths. These new observations also challenge another theory, cosmic inflation. Another possibility was that this theory, which predicted an almost instantaneous expansion of the universe in the earliest moments after the Big Bang, was wrong. The precise observations of the Webb telescope could also shine new light on alternatives to theories of gravity. These theories, which aim to describe the motions of the universe without dark matter, are strengthened by the new data. In this context, what is exciting is that alternative cosmological models exist that work in theory without dark matter. The James Webb Telescope observations also offer new perspectives on quantum cosmology, the effort to view the whole universe in terms of the laws of quantum mechanics. The temporally and spatial infinity of the universe and the multiverse are among the most interesting considerations of quantum physics. Now let us look together at what the Flamingo study has uncovered. Flamingo simulates the world, a universe, and its evolution over billions of years using the world's most powerful supercomputers. It brings groundbreaking insights. The term Flamingo stands for Full Hydro Large-Scale Structure Simulations, with all-sky mapping for the interpretation of next-generation observations. The Durham University project was part of a wider effort where scientists from various branches were trying to bring a new understanding of the universe as a whole. In other words, Flamingo was and has become a super-complicated simulation project in which hydrodynamic simulations of the very large structures in the universe were mapped to all sky and used to reinterpret the recent observations. The project has redrawn everything we know about the evolution of the universe and its structures. The shattering results from the James Webb observations came after the most important phases of simulation and analysis were completed before that. This continues today. Essentially, Webb's data is the input for a new version of the Flamingo long-term project. The study group is constantly updating these results by the leading researchers of the world. Unprecedented new insights about what the dark matter and dark energy can look like have come from combining real observations from the new space telescope with Flamingo simulations. That is, it was thus able to explain some of the key discrepancies in what current cosmological models predict. In particular, the project was able to supply new methods for matter to be distributed and clump in the universe. The main discrepancies before Flamingo were that the predictions of matter distribution and clumping were different. This might be described in plain language as the distribution of objects, such as stars and planets, in some parts of the universe. There's a very even and harmonious distribution in some, and a chaotic and wild distribution in others. Then there's the huge voids, where there's virtually nothing at all. Despite that, scientists wanted to figure out which structures and what forces are responsible for that UN-explainable distribution, and they come to different conclusions. Thanks to Flamingo, it now appears that these two results are not really in conflict with each other. Strong clumps areas follow slightly different initial conditions than empty areas, so the distribution of matter in the universe might have been a precise reflection of the state just seconds after the Big Bang, if there had been one. But Flamingo has been able to bring to the same thing two things that can't be reconciled and can't even be explained for all the structures in the universe. And some of the scientists grudgingly admit that we also must include variables like chaos and indeterminable rules. Once said by one of the most brilliant physicists of all time, Albert Einstein, "God does not play dice. God does not play dice. That is a waste of time." This is meant to imply something along the lines of, the universe did not come into being by chance. This belief led Einstein to have a crystal-clear faith in precise and predictable laws, and the theory of relativity is the result. The explanation as to which space is built, according to what rules it is, how time is passing, and what gravity is. Most of what we know in physics he helped to lay the groundwork for, and enabled the explanation of things such as gravitational waves and the expansion of the universe. Today, all astronomers and cosmologists work from these principles. The credo here is that everything is calculable and must be understood scientifically. But what if now we have gone as far as our belief in an ordered and deterministic structure of the universe? There are many forms and orders of magnitude of structures and orders of magnitude of complexity the universe may disclose, and more than we can fathom, all of which somehow fit within the immeasurable complexity and glory of the universe. Or maybe they'll never be explorable and comprehensible, or maybe the scientists of the future will figure it out. Thus, even phenomena such as dark matter and dark energy, which likely contribute a large fraction of the universe itself, cannot be explained from the available foundation of our physical theories. And there's nothing in the fact that God can do some things about which we have no scientific methods to explain. That proves he is playing dice. What it amounts to is saying that we need to go back to the playing field of mathematics and physics, because evidently God's built one or two secrets into the universe that are driving the scientists to the brink of madness. One thing is for sure, for quite some time now our science will be busy. Are we really people who know things? The first scientists probably were the first Homo sapiens, the first creatures to observe and question the world around them. These very early humans watched the stars, the seasons and natural phenomena, and learned about them and the world to understand and protect their lives. Knowers mean Homo sapiens, and although we may have been explorers for many thousands of years, we have no explanation for who or what made all this and why the world around us exists. Maybe they had already started trying to know what. The ancient Nebra sky disk and these monumental buildings reveal that there once were people who clearly understood the motions of the stars, the heavenly bodies, and somehow wished to understand their movements. A spike in science occurred when carrying with the rise of ancient civilizations, such as those in Greece, Mesopotamia, and Egypt. Mathematics in particular, as well as religious studies, continued to develop besides astronomy. Theories and experiments on the basis of which modern science had been evolved were put forth by great thinkers, as Aristotle and Archimedes. This tradition of scientific study was continued in the Middle Ages and during the Renaissance by scientists such as Galileo Galilei and Isaac Newton, who revolutionized our understanding of physics and astronomy. The past century has been an extraordinary time of scientific discoveries at an unprecedented pace. Today we have high-performance electronic telescopes and can peer billions of light-years into space. We have formulas, computers, and dozens of theories and explanations. However, this world brings us always to the beginning, and we have to understand that even in these epochs, we do not know the universe and creation that much. You like making videos like this exciting? Then subscribe. Now there are many more to come.